Okay, thank you very much, Victoria. It's a pleasure to be part of the final mood meeting and basically eat into your coffee break. So I'll try to mitigate the damage. So today I would like to talk a little bit about the genomic work within mood, and specifically the phylodynamics on respiratory viruses, which is the topic of task 4.5 in mood, which was originally focused on influenza, but for obvious reasons we had to extend it to respiratory virus in general. It's not the only task that involves phylodynamics. Also task 4.4 included some phylodynamic work, but this was more focused on arboviruses. In the interest of time, I can only present or give you an overview of a selection of work under task 4.5. So I prioritized collaborations amongst mood partners, and these are essentially some of the key actors here. Victoria herself, Chiara Poletto, also previously from INSERM, but now at Padua, Moritz Kramer from Oxford, and Simon Delecourt from ULB. And together they represent a nice mixture of genomic and modeling expertise. They also reflect my personal bias, but because they're also some of my favorite collaborators. I don't think I need to introduce this phylodynamics to this audience, but what we're essentially trying to do is reconstruct or learn about transmission dynamics through phylogenetic inference. So we essentially try to reconstruct the unobserved process of transmission based on a sample of viral genomes that you end up sampling from a number of individuals. And this is shown here for a small transmission chain, but we can basically do it at many different scales. And we generally do these type of reconstructions in a Bayesian statistical inference framework called BEAST, where we basically focus on a full probabilistic model that includes models of sequence evolution, molecular clock models, also tree generative models, and we can also incorporate trait models to look at phylogeographic inference, for example. And our contribution to this particular framework basically made up deliverable 4.4 within mood. So what we try to do here is incorporating also sampling time and sampling location, so that essentially shows that metadata is really crucial in this framework. And we've grown to learn that incorporating additional information more generally leads to more insightful analysis. For example, if you do outbreak investigations, it's very useful to combine contact tracing information with genomic information. So the more data we can integrate, the better a picture we can get. Although it's kind of challenging to do these type of integrated models. It's very relevant for COVID, I would say, because SARS-CoV-2 evolves relatively slow to other RNA viruses. So its evolutionary rate is a little bit lower than its transmission rate. So the amount of evolutionary information can be limited over short timescales, and our reconstructions can be poorly resolved. Now, there's a number of opportunities to integrate, to formally integrate additional information into the different model components of this software framework. Just to illustrate one of these, we can make, for example, the transition rates between pairs of traits or locations for phylogeography. We can make those a function of potential predictors. And that can be very useful in two ways. We can then use this to test and identify which predictors, which are the drivers of spatial spread. But it's also a way of incorporating additional information and sort of get to more resolved phylodynamic reconstructions. And this approach is actually sort of a main theme amongst many of the applications that I'm going to briefly touch upon. Now for COVID, specifically, we extended this framework to, in addition to incorporating sort of global mobility data, to also be able to accommodate individual travel history of sampled individuals. And we thought that was very important to do because the early genomes that were being sampled were frequently taken from travelers, returning travelers, in many times, in many occasions from locations that were at that time poorly represented by the genomic record. So if you incorporate that information, we saw that we can get more accurate reconstructions. And then we ended up using this framework to basically reconstruct the emergence of the virus, both in Europe and in North America. Now, one of the game changers, of course, during COVID was the massive sequencing capacity that was being developed across the globe. In the first 5 months, there were already over 100,000 genomes available. By the time of Omicron, we were already at 400,000 genomes per week. So you can imagine that creates a lot of opportunity. One of these is to do real-time molecular epidemiology, but also a lot of challenges because we suddenly have to deal with lots more information. And our framework, in particular, the statistical approach, is really struggling with this. Although it's sort of nicely statistically coherent, it's anything but fast. So we had to work on some developments to try to confront this. And now, for example, we have an online version of BEAST where you can grow an estimate as new sequence data becomes available. We can take approximations of tree space, resort to better algorithms to navigate tree space or parameter space in general, and speed up the likelihood computations. And all of that was very important to basically push these types of reconstructions towards thousands of SARS-CoV-2 genomes. And this is something that we needed to do in a study on the second wave of COVID in Europe, where the aim was to essentially disentangle the new introductions versus persistence in seeding that second wave. In this study, we also took this concept of data integration to the fullest. So we integrated mobility data in the phylogeographic models and also epi data in the sort of tree generative models. And using this, we were able to reconstruct patterns of spatio-temporal spread across Europe and quantify the number of introductions versus persistence. And as we know, that the number of new introductions over the summer was really large for most of the countries at the time. Now, moving on to alpha, I also wanted to point out some work led by Vittoria and Chiara and Benjamin Fauché from INSERM, where they focused on the silent spread of alpha and what epidemic impact this had. So here Benjamin essentially combined international mobility data, local epidemic growth, and sequencing coverage across countries to look at the silent spread of alpha, and he was able to demonstrate that this could range from days to months, but it declines with the logarithm of sequence coverage. So really pointing out the importance of genomic surveillance here. Now, the importance of early detection was also highlighted during Omicron. And I can bring up one particular study here led by Moritz Kramer and his student Joseph Tsui. The UK has done tremendous sequencing efforts during the pandemic, and they were able to work on about 50,000 genomes over the first 2 months of the BA1 invasion in England. And putting that into sort of perspective of global data, it all breaks down to many independent introductions, over 6,000 independent introductions. And the largest transmission chains were already established before Omicron was even reported in Southern Africa. So again, pointing at the importance of sort of early detection and local restriction measures. This study then also highlighted some of the drivers of the invasion dynamics in England and reconstructed the dynamics in great detail. Now, some of the work in support of some of these studies in mood also involved the development of visualization approaches for these type of reconstructions, so including interactive and animated versions, all developed by young researchers in our team. As I originally mentioned, this task was originally focusing on influenza, but then you end up in a situation where there's hardly any influenza activity. But the COVID pandemic does really provide sort of an unexpected natural experiment to assess the impact of non-pharmaceutical interventions on influenza. And that was the topic of a study led by Moritz Kramer and his student Jiwan Chen. And they basically showed where those seasonal flu lineages were being maintained during the COVID pandemic, which was mainly in Asia and Africa. So some of the sort of standard sort of source populations for influenza. And that excludes the Yamagata lineage, of course, because we know that this didn't survive the collateral effects of the COVID pandemic. Now, as I mentioned, this approach, this phylodynamic integration approach, was used in many of the studies I highlighted, both the COVID and the flu study I just pointed out. But together with the team of Vittoria and Chiara, we wanted to see if we could push this really a step further, because we have been using it to integrate covariates, but we wondered whether we could also use this to calibrate epidemic models using genomic data. So for that, we used the rich Green framework to simulate global influenza spread, and then offered these trajectories to our phylogeographic approach. And in a work that just was accepted a couple of days ago, we were able to show that this approach can really discriminate between different parameterizations of the simulation, and it massively improves over standard air transportation data. And we can get very consistent results across different variants of the seasonal influenza lineages. And then finally, before I leave you to the coffee break, I wanted to give a sort of a brief perspective on how all of this can be useful for other respiratory viruses, in this case, RSV. Now, unfortunately for RSV, the genomic data has been very limited and fragmented, but we were fortunate to be able to collaborate with people from the University of Utrecht, and they have been leading the INFORM study, which has been producing genomic sequence data in a systematic way. And although the numbers are nowhere near COVID and we don't have universal coverage, we can actually learn quite some useful insights from that genomic data. For example, showing that the driver of global spread or air transportation traffic, and in any location across the world, we see sort of a highly dynamic turnover of lineages being circulated. So it really shows a very dynamic pattern, but we can get a handle on this if we do more systematic surveillance. I think this is going to be more important with the application of the rollout of vaccines and the application of monoclonal antibodies. So with that, I'm going to conclude, and I hope I left you some time for coffee. I hope to have shown some of the uses of genomic epidemiology and how Mood has contributed to this. So I want to thank the leadership from Mood for accommodating this. And then, of course, the Horizon 2020 framework for supporting this research. Thank you.